Acoustics is a branch of physics that focuses on studying sound, how it's produced, transmitted, controlled, and received, and the effects of this process. As it applies to architecture, acoustics is the process of using building design and construction methods to harness the properties of sound to their greatest effect. Architectural acoustics involves designing a building to control how sound waves reverberate off its interior in such a way as to maximize clarity, amplifying sound in areas where it's appropriate to do so, and reducing noise levels where doing so is beneficial. Doing this involves considering several factors, including the geometry of the room and the materials used in construction, specifically their sound-absorbing or enhancing qualities. Mechanical systems can play a role, too. Fans, motors, and other mechanical components can create noises that cause unwanted distractions and may interfere with the transmission of communication. The purpose of acoustic design. Good acoustic design can serve multiple purposes, including the following: decreasing stress and anxiety levels, preserving hearing, aiding in concentration, reducing or minimizing hypertension, improving speech communication, maximizing the enjoyment of musical performances. Communication, in particular, is helped by good acoustics through the interplay of several factors. Properly designed acoustics aid in the clear transmission of verbal communication while at the same time reducing unwanted noise, thereby reducing distraction and aiding in concentration. The elimination of loud noises, moreover, can contribute to the preservation of hearing over time. Sound is the sensation perceived by the human ear resulting from rapid fluctuations in air pressure. These fluctuations are usually created by some vibrating object which sets up longitudinal wave motion in the air. There are three characteristics of audible sound. Pitch: the pitch of a sound is the frequency of its vibration. Loudness: it is the strength of the sensation received through ear. Tone quality: it is the characteristic of the sound which distinguishes it from another sound of same loudness and pitch. Sound waves: a sound wave is an air pressure disturbance that results from vibration. Sound waves are the most common example of longitudinal waves. They travel through any material medium with speed that depends on the properties of the medium. As the waves travel through air, the elements of air vibrate to produce changes in density and pressure along the direction of motion of the waves. The crests correspond to area of high pressure and troughs corresponds with rare. Sound waves are divided into three categories that cover different frequency ranges: audible wave, infrasonic wave, ultrasonic wave. Audible waves. They lie within the range of sensitivity of the human ear. They can be generated in a variety ways such as by musical instruments, human voices or loudspeakers. Infrasonic waves. They have frequencies below the audible range. Elephants can use infrasonic waves to communicate with each other, even when separated by many kilometers. Ultrasonic waves. They have frequencies above the audible range. For example, you may have used a silent whistle to retrieve your dog. The ultrasonic sound it emits is easily heard by dogs, although human cannot detect it all. Ultrasonic waves are also used in medical imaging. Sound intensity. It in a specified direction is the amount of sound energy flowing through a unit area normal to that direction. It is normally measured in watt per square meter, W/m². Intensity refers to amplitude of a sound. Wavelength. A wavelength is the distance between the same 2 points on consecutive waves. Wavelength can be measured from 2 consecutive crests or troughs. The formula for wavelength can be written in its relationship to velocity and frequency. Frequency, the speed of vibration of a sound wave, measured in cycles per second, or hertz. One complete up and down movement of the sound source is called a cycle. The number of complete cycles that the source moves per second, cycles per second or CPS, is called frequency. Frequency determines pitch. The faster the frequency, the higher the pitch. Resonance. A driving force in tune with the natural frequency, sometimes known as the resonant frequency, of an oscillator can build up larger amplitudes than the oscillator could alone. This build-up is known as resonance or sympathetic vibration. For example, put two tuning forks of equal frequencies side by side, but not touching. Strike one tuning fork so that you can hear its tone, and then suddenly silence it. you can still hear a faint tone. This is because the second tuning fork has started vibrating sympathetically. Echo. In audio signal processing and acoustics, an echo, plural echoes, is a reflection of sound, arriving at the listener sometime after the direct sound. Typical examples are the echo produced by the bottom of a well, by a building, or by the walls of an enclosed room. A true echo is a single reflection of the sound source. The time delay is the extra distance divided by the speed of sound. Reverberation. It is the persistence of sound in a particular space after the original sound is removed. A reverberation, or reverb, is created when a sound is produced in an enclosed space, causing a large number of echoes to build up and then slowly decay as the sound is absorbed by the walls and air. This is most noticeable when the sound source stops but the reflections continue, decreasing in amplitude, until they can no longer be heard. Reverberation time. The time, in seconds, required for sound pressure at a specific frequency to decay 60 decibels after the source is stopped. 60 decibels of decay is equal to 1/1,000,000th of their original level. The reverberation time of a room varies with frequency and is a function of the room volume as well as the total number of absorption units in the room. It can be determined by the Sabine equation. RT60 equals 0.049 VA, where RT60 equals reverberation time, V equals volume of the space, A equals Sabin's total room absorption that is present at a given frequency. Characteristics of speech. Any audible sound has three important characteristics: frequency, pitch, loudness, tonal quality. Any voice/instrument, various frequencies. Lowest frequency equals fundamental frequency. High frequency equals overtones or harmonics. Frequency, pitch, it is independent of intensity of loudness of sound. Pitch is a psychological phenomenon determined by frequency of a sound wave, whereas frequency is a physical quantity and can be measured. Sound is called a pure tone when it consists a single frequency, and when two or more frequencies are present it is called a complex tone. Loudness. Loudness is a physiological effect of sensation produced through the ear and depends on the intensity of sound or amount of energy present in sound waves while entering it. A note, loudness falls down as distance increases. Loudness is inversely proportional to the square of the distance from source, not applicable for semi-closed enclosures. Overtones. Distribution and intensity of overtones and GT, quality of sound plus identify one sound from another. In speech, overtones are necessary for proper intelligibility while the fundamental frequencies are not. They are responsible for naturalness of voice. Effect of reverberation on hearing. The hangover effect of one syllable on the next distorts the speech by blending the end of the first with the beginning of the second so as to mask the second syllable completely. The reverberation characteristics may give an effect of frequency distortion because of reverberation time being different for various frequencies. The intelligibility of speech refers to the accuracy with which a normal listener can understand a spoken word or phrase. Gestures are not possible in large auditorium. A product of this research was a quantitative measure for intelligibility based on articulation testing. This procedure normally consists of an announcer reading out lists of syllables, words or sentences to one or more listeners within the test enclosure. As stated before, normal connected speech can be understood even if some of the syllables are unintelligible. This is due to the fact that the listener can deduce the meaning from the context of the sentence. However, even under perfect conditions, the maximum word score normally attainable is about 95% due to unavoidable errors. A word score of 80% enables audience to understand every sentence without due effort. In a room where the word score is closer to 70%, the listener has to concentrate to understand what is said, whilst below 60% intelligibility is poor. Acoustical defects. A building is said to be acoustically efficient when an average sound rises to a suitable intensity in the every nook and corner of the room, with no distortion or echo, and then dies down rapidly before reaching of the succeeding sound wave. This condition is sought to be achieved by minimizing all acoustical defects. The probable acoustical defects can be broadly classified as follows. A. Echoes. B. Reverberation. C. Sound foci and dead spots. D. Loudness. E. Outdoor noise level. Echoes. When the sound wave is reflected by any building element, for example wall, ceiling, roof furniture and fittings, etc., it reaches the listener just after the direct wave has reached him/her. A repletion of sound is heard by the observer's ears. Hence the listener hears two distinctive sounds, one by direct sound wave and other by reflected sound wave from the same sound source. This phenomenon is termed echo formation. This can occur when the time lag between these two sound wave fronts is about 1/17 a second and causes disturbance and unpleasantness in hearing. Echo formation is encouraged by the presence of curved and smooth surfaces in the room/hall. The unpleasantness of echoes and their formation can be minimized by selecting a proper shape of the room and providing reflective surfaces of rough and porous materials. Types of echo: flutter echo, rear echo, corner echo. Flutter echo. Flutter echoes occur between hard parallel walls where the sound repeatedly bounces back and forth. They sound very nasty indeed and must be cured. It is very easy to identify where they occur by simply clapping your hands. Walk up and down the room to locate flutter echo points and mark them for treatment. Rear echo: a flat, sound-reflecting rear wall can produce echoes or unwanted, long-delayed reflections in medium to large auditoriums. Remedies: deep sound-absorbing treatment such as glass fiber blanket or board supported by furring. Large-scale irregularities or modulations to produce diffusion. Splayed surface to direct sound downwards. Corner echo: the corner echo is a specular phenomenon, created because of the bulk wave's reflections on the corner and on the specimen back wall. When two walls are at right angles, the sound waves give reflections at the corners that produce corner echo. Reverberation. Reverberation is defined as the time period in seconds taken to reduce the sound energy by 60 decibels after sound source has stopped. It depends upon the volume of room and absorption qualities of reflecting surfaces. More is the porosity and roughness of surface, more will be the friction, and hence quicker will be the loss of sound energy. Foci and dead spots. Sound waves get reflected when they are met with a barrier surface across their path of travel. If this surface is concave shaped like a domed ceiling, the reflected sound waves may pass through a common point, creating a sound of large intensity with unusual soundness. These points of unusual soundness are termed sound foci. Because reflected sound waves get concentrated at foci, some other points are created in space at which intensity of sound get negligibly small, i.e. barely audible. These are called dead spots.